Cool. Let's get started. I just want to check what I wrote down as my outline of notes of our timing. So, here we go. All right. So level 3 chem for thermochemistry, I can show you actually. So I had planned out about 10 teaching lessons to get you through all the content. We've done, you can't see. Oh, you can see. Yeah. So I put out 10 lessons. We've done the first 2. And this actually gets you a third of the way through the content, if you guys remember, because that periodic table trends is all one question. The next chunk of question is going to be these guys here, I would say. It's all about Lewis structure, shape, polarity, forces and phase changes, things like that. So that's going to be our next question. And then our final question is going to be on the enthalpy sort of calculation stuff. So that's how I've blocked it out, and I've put out what weeks are roughly going to be things. I think, so this week I'll just do Lewis structures for you guys. Next week I'll do shapes. I figured you guys probably want some practice just recapping Lewis structures because you can't really figure out the shape without the Lewis structure. I'll do a lesson on polarity, forces and phases, just so you guys know what that question is. Enthalpy. 6 and 7, I'll do enthalpy calculations. I think you guys probably would need 2 weeks to kind of cover that. It'll probably be 1 week of teaching. The second week, you guys have just processing time. And then Hess's law, again, will probably be a 2-week thing. I'll teach it in week 8. You'll have probably week 9 with no tutorial, so you can practice that. And then week 10, I'll just wrap it up with entropy.
Does Hess's law what's the word, link into Gibbs free energy at all?
Yes.
I thought so, yeah.
So that's where the entropy lesson's coming in.
Yeah, okay.
So that's our plan for this term. And so we'll finish it just in time for you guys to go on break. And then term 4, my plan is that you can just kind of use that as study time and things like that. So let's talk about Lewis structures. With Lewis structures, I'll recap the stuff from level 2. Yes, no? Or do you guys feel like I could just jump into level 3? Recap? Slight recap. All right, now I gotta remember what I want to talk about. Okay, so with the Lewis structures, we are using this for molecules. And it's doing that thing again, isn't it? You guys see that okay? Yeah. So with Lewis structure, this is specifically for things that are molecules. I'm going to unplug and replug in my camera for a second because that's blinking. All right, so that's specifically for molecules. If you guys remember last time when you did structure and bonding, there were the 4 types of solid. There was metals, covalent networks, covalent molecular, and ionic compounds. And then with the Lewis structures, you only use that for the covalent molecular, correct? So we are specifically talking about molecules. Lewis structures are a way for us to draw and communicate across what that molecule is. And if we know what that molecule looks like in its Lewis structure, we can then jump to explain the shape of it. So some things to keep in mind with Lewis structures. There's 2 ways that you can go about figuring out Lewis structures. One I like to call the guess and check method, and the other one is the mathematical method. I teach both at level 2 because I think it's good for students to have options, but the one that's better going into level 3 is the guess and check method. And the reason why is because at level 3, you're going to do stuff that's extended octet, stuff that are bigger molecules. And since you're doing bigger molecule stuff, you really need to be able to do that kind of guess and check and move things around instead of just doing mathematically. Because with the larger molecules, they can actually have more than 4 bonds. And they can also have the option of sometimes doing double bonds or not doing double bonds and things like that. So it's just a little bit more complex, and so I figure the guess and check way is better. So I'll go through that as a refresher. I'm just trying to think what's a good molecule. Probably carbon dioxide. All right. So when we are thinking about carbon dioxide, in fact, I'll use my erasable markers because then we can actually move things around. There we go. All right. So if I'm dealing with carbon dioxide, we know that's CO2. My first step when I try to figure out my Lewis structures is I need to figure out how many electrons are there that I'm working with. So we use the periodic table to figure that out. Remember that with Lewis structures, we're only concerned about the valence electrons. So we're going to be looking at those columns to figure out what group they are in. So if I was to look at carbon on the periodic table, it is in group 14. So that tells me it has 4 valence electrons that I'm working with. Are we okay with how I got that number? All right. The other thing you need to factor in is how many atoms we have of that, how many atoms are in that molecule. So when I look at carbon, there's only the 1 molecule, so I'm just going to multiply that by 1. So carbon's contributing 4 valence electrons. Cool? All right. Second thing I think about is oxygen. Again, I look at the periodic table. I see it's in group 16, so that tells me 6 valence electrons. Again, I look at the molecule to see how many oxygens I have. I see that there's 2, so I'm multiplying by 2. So I get 12 electrons. So total, I have 16 electrons to work with. It is really important that you guys are doing a count of how many electrons are there because we don't want to accidentally create or destroy matter. So we're going to keep a check on the count. Now for this guess and check method, the way you start off is that you put your center atom down and you assume there has to be at least 1 bond to the other atoms to hold everything together as a molecule. When you're trying to decide what is your center atom, there's several different things you can do. The first thing is you can look at to see what the formula is, because usually if you only have one of it and multiple of other stuff, then that's going to be the center. So if I look and I see carbon dioxide, I have 2 oxygens and 1 carbon, so that suggests to me that carbon's my central atom. The other thing I can do is look to see how many bonds that each atom is possible to make. And ideally you want to pick something that can do 4 or 3 bonds. Those are more likely to be the central atom because they can do more bonding. It's unlikely to be something like oxygen because it can only fit 2 bonds in there. And that's why when we talked about organic chemistry, carbon is such an important molecule for the building of life because it can do the maximum amount of bonds that are possible. So if I was to draw these atoms, hi again. If I was to draw these atoms as their Lewis structure, I just want to show you what I mean by how many bonds you can do. So that's carbon, 4 valence electrons. And so what this means is that it can have 4 possible sites to make bonds with something else. Does that make sense? So that's why carbon's good. There's 4 spots for it to bond. And anything in group 14 could do that. So in theory, we could have silicon-based life because silicon does the same thing. It's just not as readily available. Oxygen, on the other hand, has 6. So that's 1, 2, 3, 4, 5, 6. I'm just placing them randomly to show you that this guy here only has the space to do 2 bonds. So it's not as versatile for that reason. Nitrogen's generally pretty good as a building block because it can do 3, that sort of stuff. So that's how I kind of look at that information and use that to help me figure out what my center atom's going to be. So from that information, I figured out that carbon is going to be my center atom. Oxygens are going to be outside because usually most of these molecules are some symmetry in there. And I need to make the assumption that there's going to be at least 1 bond to hold everything together. So I'm doing a line there, like that, assuming everything's being held together. Remember that line is a way to represent 2 electrons. I highly suggest you do lines instead of just doing dots because it helps you distinguish what's what. Also, when you're explaining shape, you want to be able to talk about paired and unpaired electrons, and so that helps you distinguish it when you're looking at it really quickly. So that's the first thing I do. The second thing I'm going to do is keep track of the total number of electrons I've used. So far, I have 1, 2, 3, 4 that are being used. And you can do a little tally on the side, or you can do a little subtraction from your main total. Just some way to keep track of the number would be my suggestion. So I'm just going to go 1, 2, 3, 4 because we don't want to create or destroy matter. So that's my next step. If I've used up 4 electrons, I then have how many left over? 12. Okay. With this guess and check method, you go outside, going in, and you're going to use all the electrons on the outside first and then fill in the center atom. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I've used up all my 12. So all the electrons are now being used.
So
Okay.
the 4 dots, the 4 lines we put there are from the bonds. And
Yeah, so this 4 is coming from the lines, and then I've gotten another 12 from the dots that I put around, and the dots show that those aren't in bonds. So if you want, I can keep my tally going.
Right.
That's 12. So I've used up all my electrons, that's good. No, sorry, 16 total. That's good. Then what you want to do is check to see, does everyone fill the octet rule? And Yada's already like shaking her head no, because she can count. So oxygen on that side's fine, oxygen on this side's fine, carbon in the center only has 4, so it's not okay. This is why I say it's the guess and check method. I've guessed where things are supposed to go. I've double checked it. I realize it doesn't work, so I need to start shifting electrons. What we're going to do is take these unpaired electrons on oxygen and shift it to be a bond between the oxygen and carbon. So that's what I'm going to do. Take these 2 electrons. Doesn't matter from where. I just like things to look symmetrical. And I'm putting them now in as a double bond. The number of electrons on oxygen has not changed because all I've done is shifted it into a bond. So if I count, it's still 2, 4, 6, 8. If I check this guy, it's still 2, 4, 6, 8. And now when I check carbon, it has 2, 4, 6, 8. That's why I'm saying I haven't created or destroyed matter. I've just moved the electrons around. And that's how we're able to generate more electrons to fulfill everyone's octet rule.
So you want every single one of the things in the line to have matching amounts attached to them?
What do you mean?
So like each one should have 8.
Yeah, so
8 different electrons, sorry.
just 8 electrons total, yeah, in each atom. That's for the simple molecules. We're going to get to larger molecules, and those ones, now that we know about subshells and how it goes up and down and things like that, we now know that there's certain atoms that can hold more electrons. So with the level 3 stuff, you'll be able to see extended octets, and those extended octets can go up to 10 and 12. I'm trying to think if it can go up to 16. I don't think so. I have to double check my notes. But that's kind of the first thing to kind of keep in mind. Are we okay with that? Charlie, you looked like you had a question. Huh? Okay, so you're fine. All right. Do you guys want to see another example of this?
Yeah.
Okay, I'm just trying to think of a molecule that would have like double bonds.
Oh, actually,
No, it's too easy. I'm gonna do something with, actually, let me do one that's like an organic molecule because it might be more interesting.
Oh, no.
All right, C2H. Trying to think how I'll do it. Oh no, that's not a good one. Actually, let me do like ethanol. Would that be interesting?
Yes, I like ethanol.
CH3COOH. Let's do ethanol. It's a big molecule. It has a double bond. Figured that'd be a fun one to do. Actually, that might be too complicated.
Okay, never mind.
Yeah, well, because then I have to. Yeah, because it's not like a logical one to do. Let's not do that one. I'm just trying to think of one. Maybe I'll look in the book to find one. Because I want something with like a double or triple bond.
Don't iron, no, never mind.
Let me find something in the book. Where are you, Lewis structures? Ah, 29. That's explaining how it does it. Oh yeah, that one could work. All right. We'll do CH2O. All right. So again, we do the same process that we did before. Go through, count the number of atoms, count how many electrons they're providing. So carbon provides 4. There's only one of it. So there's 4 electrons coming from the carbon. Hydrogen on the periodic table is in group 1. So it only provides 1 electron. I have 2 hydrogens there. So that gives me a total of 2. And then oxygen is in group 16. That gives me 6 electrons. There's only 1 there. So that gives me 6 total from that one. Cool. All right. Add them all together, and I'm working with only 12 electrons now. Center atom, probably carbon. And then assume everybody has to have at least 1 bond. So carbon, oxygen, hydrogen, hydrogen. All right, and so far from that, I've used 2, 4, 6. Oh, I did not do that well, did I? It should be aligned over there. Everybody happy with how I got that set up? Charlie? Okay. Now what I'm going to do is start from the outside going in to try to use up my electrons. So I should have 6 more electrons left, according to my count. 1, 2, 3, 4, 5, 6. Okay. Hydrogen doesn't need any more because hydrogen already has the 2, because remember it's an exception to the rule. Hydrogen over here, 2. It's fine. When I look at this information here, carbon is not okay because carbon only has 3 electrons. So we're doing the same thing in shifting electrons. I know I must have to shift them off the oxygen because there's nothing to shift from the hydrogens. So that's where the double bond's from. And you guys know that as an aldehyde. And that's how I do it. That's from last year. That was last year's stuff. All right, do you guys feel like you need another example, or are you okay? You're okay? All right, so my question for you guys now is, do you want me to go into the larger molecules, or do you want to have a chance to practice this first?
I just want to go.
You want to go through it? What's the rest of it?
I remember this one lot.
You remember this? All right, but it's the whole...
I remember finding it very confusing, which is right. I think
All right, do you guys need some time just to practice the first
I reckon
bit?
just give us the sheet to go home and it'll be fine.
Well, what do you think? Keep going, or you want to practice this? Keep going? All right, people on the back table, want me just to keep going? Okay, happy to do that. Okay, so 2, 4, 6, 8, 10, 12. Yeah, I was right. 12 is higher. Okay. So with the level 3 chemistry, now what you got to be mindful of is that things can get bigger and more complicated. When we are particularly looking at elements such as sulfur and phosphorus, they can do that extended octet, and so we are not bound by the octet rule anymore, so they can actually get higher number of electrons, and they can actually do more bonding as well. So let me go through some examples of what they would look like, and again, the process is exactly the same. So if I have PCl5, you do the same thing that you would do before to set it up. Don't rush these guys. I can probably look at them and tell, but especially with the extended octet and the level 3 stuff, I tend to still work my way through it instead of just kind of going straight into it. The level 2 stuff is generally pretty simple, and it's all following the octet rule, so it's very easy to kind of look at it and tell what's supposed to happen. But the level 3 stuff, because you can have extra electrons, you need to know where they go. So again, go through the same process of counting electrons. So phosphorus, when I look at it on the periodic table, it's in group 15, so that's 5 electrons. I only have 1, so that gives me 5 to work with. And chlorine is in group 17, so that gives me 7 electrons. I have 5 chlorines now, so that gives me 35. So total number of electrons I'm working with is 40. So this is what I'm saying about the extended octet. We're gonna have a lot more electrons to work with. Again, when I'm thinking about this, I need to think about, okay, what's gonna be my central atom? Very unlikely to be chlorine because chlorine only has that one spot to fit for bonding. And so phosphorus is probably going to be the one that I should put in the center. So I'll put phosphorus in. Now I need to attach all of those chlorines. And since phosphorus is a bigger molecule, it can do the extended octet. And so now it can actually hold more than just 4 atoms. So I'm going to show it as having the 5 chlorines around it, each one with a bond. And if I was again doing the math to see how many I've used, right now I've used 10 electrons. So what I have left over from my 40 is 30. If I've done my math correctly. And then we start again, outside going in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. All of them are accounted for. So I know that structure's done. And phosphorus is fine with 5 or with 10. Now, sometimes when you're doing this, you're going to get spare leftover electrons, and when you do that, you then put them on the center atom. So I'll try to find you guys an example that does that. Let's see. Giving a lot of instructions. Let me get the level 3 book and see if they have an example in there that I like. Any questions so far about that? It's pretty straightforward. I like the guess and check method, to be honest, because it kind of forces you to move things around. Yeah. So be careful with the exam, because when I was doing exam marking, actually no, you're fine, because it's I know the science ones, they scan it, and so they don't have to worry about you making corrections to return it.
Is it?
Yeah, so I don't know if they're going to be like not letting you use pencil.
Exactly, well, not like when you cross something out.
No. So you know how exams you couldn't get it remarked if you wrote in pencil?
Yeah.
Because you could, in theory, like get your exam paper returned to you, you then erase it, and then you rewrite it, and so then send it back and get it remarked. So they didn't accept anything with pencil. And I noticed erasable pen because I knew what it looks like because the ink's different. And so I've actually just put that down as a note so that way it wasn't allowed to get remarked. I don't know if the kid realized that or was trying to pull a fast one. But apparently now they, instead of the exam markers hand marking them, they're all scanned and then the markers mark on the computer. So they don't need to worry about containing it anymore. Because have you ever noticed when you're looking at your exam papers how there's like these red pens that kind of like cross out if you leave a blank page and then they put like little tallies? That's what we call containing as an exam marker. It's so that way if you send something back to get remarked, we can tell if you added anything that.
I've never gotten my exams papers back after they've been marked. I just kind of accept it.
Because they'll like circle things as well on your page.
Or like the sentences, they put like.
Yeah. So what we have to do is contain it, is what we. So that way, if it ever gets sent back to get remarked, we can then tell if you have added something to it.
It's like you can even like put arrows above.
Yeah, so what we're supposed to do is contain it and circle it so that way it indicates. But then students could get around that technically by just like circling it with a red pen. Make it look like it was part of what the original containing was. But now it's all done electronically, so it doesn't matter, I don't think. I want to find something that has like a double bond. Ooh, we can do sulfur.
Haven't we done something similar to this before? Like I remember last year in Mr. Jim's class, I was like doing 4 from 14, and then you guys were like, no, it's not like that. And I was like, oh, okay. I'm thinking.
We did this
We did it most.
Okay.
Yeah.
I think I've definitely been at some point
Because we were
confusing
gonna
real
do this
instructions
exam,
with something
remember?
else.
Did you guys not do it?
No, because
It's like the
program.
Oh, right, yeah. I'm just gonna try to find one that I like with a double bond. There we go, that's one I like. All right, cool. Here's another one. So let's do, so you guys can see what you do if you have extra electrons. E, F, 4. I'll give you guys 2 more examples because I want you guys just to see the variety of it. Okay, so here is our next molecule to do. I'm trying to see where Xe is on the
It's
periodic
8,
table.
right?
Is it 8? Oh, because it's a noble gas.
Because it's 8, yeah, noble gas.
I don't even know what the name of that element is.
It's xenon, isn't it?
No, I thought Xeon was something else.
I wouldn't know.
No, I'm thinking neon.
Okay. Excelsior.
All right, that's in group 18, so it's 8 electrons. All right, so that one has 8 electrons. Oops. There's only 1, so that gives me 8 to work with. Fluorine's in group 17, so that's 7 times 4, that's 28. Did I do that math right?
Yeah.
Okay. I'm not always the best at mental math.
So 36.
Yes. So 36 electrons to work with. All right. Xeon's going in the middle. You guys gonna see me again? Because I keep accidentally hitting the mouse. All right. So Xeon goes in the middle. I assume everything, oh, let me move that down a little bit so it's not as in the way. Assume everything needs to have 1 bond. Like that. I have taken care of 4 bonds times 2, 8 electrons. So 36 minus 8 is, I have 28 left. Do we all agree with me?
Yeah.
Okay. Next thing I do is drop down those remaining electrons. We start outside going in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So I have 24. So I subtract away those 24. I have 4 leftover electrons. All right? So now what I'm going to do is I'm going to put them in the center atom. I'll grab a different color. I'm trying to think what color I haven't used yet. Green. Doesn't really matter where you put them. You just got to show me that you have some electrons on there. So that takes care of the final 4.
So you just put it there even if it doesn't need it?
Yeah, because it needs to go somewhere. Because we can't create or destroy matter. That's what we need to be really careful of. Remember that with the Xeon, it is a larger atom, so it can do that extended octet. So with the extended octet, these center atoms can have 8, it can have 10, or it can have 12, and it'll be fine.
Yeah.
So in this case, the Xeon has 2, 4, 6, 8, 10, 12, so it's fine with that extended number. The main thing that people mess up is that they don't count their electrons properly, and then they add electrons where they're not supposed to be. Or they forget them. Or they create random double bonds that shouldn't be there.
Yeah.
Oh,
I think our teacher before used to say do a tally.
Yeah, it's worthwhile to do a tally.
Yeah.
Just do a count.
wait, mess
Because
up.
the thing is, if you mess up the Lewis structures, it's going to snowball, and you're going to get the shape wrong.
Yeah.
Yeah? All right,
Why did we put electrons in the middle?
because we still have 4 electrons left.
We had 4 electrons.
Yeah, so they need to go somewhere, and they're going to go in the middle.
Okay. 2, 4, 6.
All right, I'll give you guys a few more examples just so you can kind of see what to do in lots of different cases.
Don't we get extra?
No, we shouldn't.
We've got 24 on the outside, and we've got 8 on the one on the inside.
Double check my math.
Maybe I'm just having a counting.
That's 10. No, that's 8. 2, 4, 6, 8.
And then we've got.
And that was 28. And then we had 24. So that was 4 left over.
Oh wait, no, that's because I was counting off of 28 for some reason.
Okay. This is why I'm saying it's just going to be a basic math issue if you muck this up. Double and triple check things because, like I said, it's going to snowball and you're going to get the shape wrong.
Yeah.
And then there's nothing we can do to help you if you get the shape wrong. All right, especially as an exam marker, we try, but there's certain things that happen that we can't help. All right, here's another example. We have PCl3O. I'm just giving you guys a nice variety of things to look at just because I want you to see what to do in different situations. So phosphorus, looking at the periodic table, that guy is 5. Only got 1, so that's 5. Chlorine, 7 on the periodic table, 7 in its group. There's 3 of them, gives us 21. And then oxygen is 6, only have 1, that gives us 6. Do some math. Well, carry the 1, 32. Did I do all my mental math correctly?
Yeah.
Okay. All right, phosphorus is the one that's going to go in the center. Assume everybody has 1 bond. Yeah, this is a good one to show you guys, actually. That gives me 8 electrons. So 32 minus 8 is 24. All right, let's start putting them down. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And phosphorus right now has 4. But with the extended octet, it can actually do more bonding because remember, it can go upwards. So what I can do actually is remove 2 of those electrons if I want and form a double bond.
You have to say you have to?
The answer in the book says that. I'm trying to think if there is a reasoning for it because technically the other one works too. Because the other one fits the octet rule. So I want to see if there's a reason.
Wait, so is the trend that if you've got an oxygen, you want to put double bonds, or is that?
So here's what I want to show you, and I think that's probably why they would accept multiple answers.
Right.
This is the example for sulfur trioxide, and you see how there's 3 different accepted answers here?
Yeah.
And that has to do with the fact that that sulfur can have 8 and be stable, have 10 and be stable, and have 12 and be stable. So my guess is that it should be stable. I can check the SciPad though, because maybe there's a scientific reason to why you want that double bond there. It could have to be about filling their subshells, would be my guess, if there's a reason. I haven't come across it though. Let's see. Yeah, I'm looking at this, it looks like it's because you want to fill that 3D shell. So if I'm looking at the SciPad work that you have, and phosphorus preferring that extended octet, my guess is that it has to do with the fact that if it's got 10 electrons, it's going to fill that 3D. So I think that's probably why that's more likely to be the answer. That's a good question. So I think what they will probably give you is stuff that's straightforward, that you like, if it fits the conditions, it will be fine. So looking at this here, this is why I wanted to show you guys it, the sulfur trioxide. When we look at it, you see how these 3 are all accepted answers. And the reason why all 3 of them are accepted answers is because that sulfur is stable in multiple states. It's stable if it has 8 electrons, it's stable if it has 10, it's stable if it has 12. So my assumption would be if all the other atoms are stable, which is what we saw initially, this guy here, like that. And I think I actually had a debate with another chemistry teacher because it wasn't the right answer listed on the marking schedule, but it still was technically correct with what we teach you, that they should accept it in the marking scheme. Because when you look at it, it fits the criteria for everybody. All we've done is we've moved these electrons to give phosphorus to 10. So my assumption would be that they should accept the other one as an answer, even though this is the technicality, the right answer, which I'm guessing has to do with the fact that the 3D shell is now full. I would assume that NZQA would accept that as an answer because it is technically correct. So
it's like personal preference almost.
yeah, but double check what you're working with, because obviously when you're doing the work, in some cases like this one here, it wouldn't make sense to have any double bonds because you have those lone pairs of electrons. If I had something else there, yeah, it just really depends. So you guys got to do the practice to kind of see the different examples. That's the thing with Lewis structures. I think this must have come up last year when I had a mock exam, because I remember the other chemistry teacher coming over and pointing it out to me and saying, I don't want to mark this student wrong because technically it follows the conditions that we teach them. And I said, yeah, I give them the point. The other thing to keep in mind is if you have any ions, that you need to put them in square brackets. So you can do Lewis structures with ions. I'll just quickly draw one out so you can see it. I'm not going to do all the working behind it. So let's say I had PCl6 with a minus on there. You do the same working as you would before. You look up phosphorus, that one has 5. You look up chlorine, that one has 7. You multiply it out just the same way that you would do. So that's 5. That's 42. The thing you have to remember is that since this is an ion, you're going to add an extra electron because it's negatively charged. If it was a positive ion, you would take one of the electrons away. So I'm adding an extra electron for that negative charge there. So that actually gets me up to 48 electrons. Just keep that in mind. When you go out to then draw it, I'm just going to quickly draw it and not actually do all the working behind it. Just to kind of show you what the structure looks like. This one's pretty straightforward actually, because when you're looking at it, it makes sense. So, yes, you're right. Oh, I did the other one. I need to make space for you. There we go. So that's my Lewis structure. When you're dealing with ions, just remember you put it into square brackets and you put the charge on the outside. I think they might have given you some of these last year for.
Yeah, they did.
But you see it more in level 3. Cool.
Yeah.
What questions do you guys have? Sounds like it's silent, so I'm guessing none. The thing with Lewis structures is that it's very easy to make a mistake because it's let me backtrack. With Lewis structures, it's really easy to be overconfident with them and to rush yourself and just go, oh yeah, looking at that molecule, this is what I'm going to draw. And then, especially with that extended octet, you might miss a double bond somewhere, or you might miss some lone pairs of electrons that are in the center atom. So it pays just to double check things. It pays just to make sure you know the electron count, and just at the bare minimum, check to make sure you have the right number of electrons. Okay? And I'm going to keep saying it. If you get the Lewis structure wrong, it's going to snowball. And it's going to snowball very, very badly. So it's worthwhile spending that extra 5 minutes double checking it before you start writing your essay on the shape. Okay? Cool. Do you guys need to see any more examples? You think you're okay?
Yeah,
I think it's probably fine.
Was that everything for today?
Yeah, that's all I wanted to cover for today. Next week, I'll do shapes. I'll post onto Google Classroom what pages of the SciPad to work on. Next week, I'll give you guys the next fortnight question. With that fortnight question, I'll give you not only a Lewis structure, but also a shape question, so it's going to be due in 2 weeks. And you'll be able to do shapes anyway. I'll post onto Google Classroom what SciPad pages to do, but I'll say it right now if you guys want to know. It will be, you will do page 29 to 43 would be the pages in the SciPad. Those are the ones that are practicing Lewis structures and just Lewis structures, not going into shapes.
It shapes like the kitchen eagle.
Yeah, but the shapes are going to get real ugly because there's going to be a lot of them.
I was gonna say, give me my shit.
I lost my basic 6.
Yeah, there's going to be a lot more now, and they're going to have really crazy names, like, what was it, seesaw. There's one that looks like a seashell, like a seesaw, like at the playground.
Yeah.
Yeah.
I just
Alright.
like shapes that.
So next week we do
Yeah, so next week we'll do the shapes. Did you guys, I know most of you guys talked about liking tutorial times. We have several options. We can do it in the Friday, if you guys want to do the Friday. I'm happy for us to do it before or after school, because I think most of you guys said Monday before school, or I think the other time that most people said was Wednesday after school, and I'm happy to run 2 tutorial sessions just to cover everyone's bases, but I want to check with you guys what you prefer. So our options are basically, we run it on Friday, or we do, I offer 2 tutorial sessions for people. What would you prefer?
I like Friday.
You-
Cause like I don't have any other classes usually last period.
Okay.
Yeah, I think Fridays are good.
So you guys happy to do Friday last period? I know a lot of teachers try not to schedule things last period because most kids want to just go home.
Yeah, you can do period 1 and 2.
Yeah.
So that's why it's not.
Okay. So should I just schedule the tutorial for, oh, the only thing I need to make sure is that it doesn't clash with anything with STEM.
Yeah.
Because my STEM guest speakers sometimes tell me what time, or they need to tell me what time that works.
Yeah.
Yeah. But I don't think I have anyone lined up for next week.
Does this mean we're not doing it twice now?
Doesn't sound like it. I was also gonna say for the STEM, because I know you guys, most of you guys missed it today, what my plan is for this term. So I just want to give you guys the people that I've booked so far. So the 12th of August, I booked my friend Brittany, who is a neuroscientist. On September 9th, I've booked my friend Julia, who first trained as a pharmacist and then has now retrained as a doctor. So she's currently at medical school. So that's really interesting. You'll be able to talk to her both about pharmacy and med school. And she also studies down in Otago, and she did her pharmacy up in Auckland. So she'll be able to tell you about more universities. I've booked for the 30th, which is the last week of term, my friend, or my partner's friend, Bronwyn, and she's a pediatrician. So that's going to be in the last week of term.
I'm not gonna use this.
I'll record it. I'll record it. The other things that I put on my agenda is I would like to do a session with you guys about how NCA exams get marked, so you guys have some insight into what happens. And then I was curious if you guys would be interested for me to take one of the sessions and for me to kind of talk specifically about my career pathway, because I know I gave you an overview about uni, but I haven't actually talked about what I did. So I don't know if you guys would be interested in hearing what I did. Yeah? Okay. Cool. All right, that's all. You guys can head off.
I'm still